My name is Shreyas and I'm part of Group 11. So, for our CS 5370 scheduling algorithms class, the topic we have chosen is the bus and train driver scheduling. So, our group consists of three members, which is Mahakbai, Shivam, and Shreyas, myself, Shreyas. So, over the next hour, we're going to venture into public part of transport operations that most passengers never think about, but that absolutely determines whether their bus or train shows up on time or whether their fares stay affordable. That hidden engine is called driver scheduling. So what is exactly driver scheduling? So driver scheduling problem is basically assigning drivers to cover or schedule vehicle trips for a day's operation. So, the formal definition of driver scheduling is basically driver scheduling is a disciplined process of allocating living, breathing, qualified human beings, our bus drivers, our train drivers, or tram motormen to operate every single vehicle trip that appears on a public timetable for a given operating day. So imagine opening a Monday timetable in London. For this topic, we are going to be focusing exclusively on UK and London. So you'll see thousands of rows at different timings. So take for example at 5 8 p.m. from one location Barking to another location Tower Hill, and then another ride from 5:14 to the same location and another time, suppose 5:20, to the same location. And then you flip the bus pages and you have different routes. So you can have like a route 25, for example. You can have a bus reaching route say 37 at some amount of time, suppose say 5:45 p.m., and so on. So behind every row sits a driver assignment, or the service does not roll. So why is this such a big deal? Because labor is a single largest controllable cost in transit. Rough global numbers: diesel fuels maybe 15%, electric traction a bit less, depreciation on vehicles and infrastructure is about 20 to 25%, administration and overhead is about 10%, and then labor, wages, overtime, holiday pay, person's contribution swallows the rest. So in UK's big metropolitan bus operations, official accounts show that driver wages hover at 40 to 45% of the operating expenditure. At National Express West Midland, for instance, 2023 accounts list about 203 Great British pounds million in staff costs cut out of 465 million. So if we can cut even 2% from that figure through better scheduling, we unlock over 4 million money that could buy 35 zero emission double deckers or freeze fares for a year. So you can see how big of a difference that could make for the general public. But scheduling staff is vastly harder than scheduling vehicles. A diesel bus, for example, will happily circle all day if you keep it fuel, but a human driver cannot. Hard safety and legal limits apply. So UK's domestic bus regulations say that no more than 5 hours 30 minutes of continuous driving without a break, and no more than 10 hours duty spread over and at least 30 minutes of paid meal break on a shift longer than 8 hours. So these are very basic health concerns which have been set by the authorities in UK, and the UK the Drivers Association must ensure that these regulations are being met. So the Rail and Drivers Guard rulebook is even stricter. A maximum of 9 hours of actual driving, 12 hours sign on to sign off, a minimum of 12 hours rest between duties plus certifications per route per rolling stock class. And if you breach these caps, you risk fines, union disputes, or worse, fatigue staff that control a vehicle which is super heavy. So you don't want to, you want to make sure your driver is not really fatigued, as that can cause a big problem and an accident, which you don't want. So yet the vehicles they drive may need to operate 10, 19 to 20 hours per day. Think of a night bus or a late sleeper bus. Therefore, one vehicle's diagram gets split across multiple driver shifts. In a mid-sized UK city, that could mean 900 weekday bus blocks with 1300 separate driver shifts once breaks and handovers are factored in. Add a local Add a layer of local flavor. Every region negotiates slightly different work rules. London, for example, contracts a pay fixed turnaround allowance at terminal so that drivers can reset their Wayfair ticket machines. Edinburgh is a slightly different example. What Edinburgh does is that, yeah, so sorry, so yeah, Edinburgh is slightly different, as I said. It has an agreement where unpaid breaks longer than they forbid unpaid breaks longer than 20 minutes. Singapore SPS transit service places a cap on total split shift spread over 13 hours. Even if the paid hours are only 7, same mathematical DNA, widely diverging final rosters. So, for clarity, today I'm going to illustrate primarily UK examples because chapter 51 of this book, the Handbook of Scheduling, builds its case study on the British data. So that's why we're focusing exclusively on the British data. But these do kind of generally apply to all the European cities. So here's our roadmap for our presentation today. Slide 2 will talk about the vocabulary, relief opportunity spread over so that everyone is in same page. Then slide 3 is slightly more about the functions, and so it's going to go on like that. And by the end of the presentation, I hope you'll appreciate driver scheduling. It's a very thought of process. A lot of work goes into this, so it's not something which is very easy to, it might look easy, but it's not easy to actually implement it. So let's get started. Yeah. So what are the key terminologies and concepts? Relief, points, and opportunities. So every specialty has its jargon and driver scheduling is no exception. But this jargon isn't there to just intimidate it precisely. Let's unpack it in 8 simple fundamental terms. So the first, relief point, a fixed geographic location declared suitable for a driver change. It must have safe pedestrian access, toilets within reach, and ideally a staff lounge or at least an street shelter. In bus operations, major terminals, out of service layover bays, and certain busy shops become relief points. On rail, almost every station could serve, but time, timetable margins, and route knowledge constraints prune the list. So, relief opportunity. Think of this as a timestamp attached to an RP. If the 7:43 p.m. bus, which is on route 25, for example, arrives at Oxford Circus at 8:12 p.m., that specific 8:12 event is an RO. The very same location at 8:18 for the next bus is a separate arrow. So, workpiece. What is a workpiece? A segment of vehicle work between two relief opportunities. These are the building blocks that must be assigned to drivers. So, next is the spell. A driver's continuous driving stint on one vehicle without dismounting in bus that often equals to one work piece. In a rail, a spell can include two back-to-back pieces if the train reverses quickly and the driver stays in cab. Breaks. These punctuate spells. Join up break in our micro break. Yeah. So UK bus law demands that meal break should fall within a window. Every 8 hours, you must have a meal break. Otherwise, it's you must pay the violation fines. So sign on, sign off. Official duty start and finish time. At sign on, driver completes a breath analyzer, checks duty cards, maybe does a walk around safety check. At sign off, they cash in the ticket machine, hand keys to the depot controller, and a digital timesheet. Knowing these events matter because payroll uses them, not just driving time, to calculate hours spread over. The elapsed clock time from sign on to sign off, inclusive of breaks, dead running in passengers, and any paid admin task. So the rules caps, the regulation cap is spread over 10 hours for domestic bus, 12 hours for European rail, and yeah. So the duty shift. A duty bus uh, is approximately 6 hours, 6 or equal to 6 hours, and sometimes reserve or spare shifts left blank so depot managers can plug gaps. So let's give an example for you to understand this better. So picture a Cardiff bus duty 415. Sign on is at 5:55 p.m. Depot. Dead run 8 minutes to city center. Spell 1 drive route 17 to Ely. Join breakup 6 minutes. Spell 2 drive route 17. Meal break 40 minutes in the city crew room. Spell 3 drive duplicate to Fairwater. Sign off is at 1:45. Spread over is 7 hours 50 minutes. 3 spells, 2 breaks, 6 work pieces if we slice each inbound and outbound separately. That granular labeling is what allows optimization software to mix and match pieces while always respecting legal needs. Why such obsession? Because later, when our algorithm tries to minimize cost, it needs the crisp binary answers to questions like, does this candidate shift exceed the maximum spread over, or can we insert a meal break at this RO without violating the meal window? If the foundation terminology is fuzzy, the constraint logic breaks. So, for the slide 3, we have scheduling objectives and challenges. So, what's the primary goal? So, the goal is to minimize the number of driver shift needed to cover all work. Basically, use fewer drivers as possible to reduce cost, which is ultimately the goal. So, cost versus count. Sometimes a simple shift count isn't best. Using many short part time shifts might formally reduce the shifts but raise cost. Thus, a common objective is minimizing the overall total cost of all shifts. Legal and contractual rules. Many rules constrain shift, maximum driving hours, required breaks, spread over limits, etc., making scheduling a complex constraint problem. So, problem scale. Even a medium sized transit operation generates a huge search space of possible shifts, allowing shorter spells or more relief options can explode the number of possible shifts exponentially. So what's the goal? So goal is to reduce the number of drivers, basically to reduce the number of cost, to reduce the cost. So yeah, and we have the planning and scheduling time frames. Strategic planning. It involves a long-term planning in about 5 years ahead. High-level planning done far advance, like I said, with approximate data. It generates a rough driver schedules for what if scenarios. For example, a train company bidding on a 15-year franchise or a bus operator tendering for a new contract. Operation scheduling. The regular schedule updates done few times a year. Final driver schedules are produced a few months before implementation. These are thoroughly checked for rule compliance and heavily optimized, since they will be used repeatedly until the next timetable change. Short term scheduling, last minute or temporary schedule adjustments for construction projects, special events, holidays. The goal here is a minimal deviation, keeping as much of the only original schedule as possible, because these schedules are only used briefly, so extensive optimization is less worthwhile. Offline versus online. The above offline scheduling planning done ahead of operation with notional shifts. Online scheduling, it refers to the real time reassignment during the day of the operation done by the operator. This is much more complex and not covered here in this topic. Now we have the relationship to planning, other planning tasks. Strategic planning. So, like I had covered here, strategic planning is basically a long term planning, and yeah, so this is just the same slide as before. And now we have the relationship to other planning tasks. So, you have different tasks like operation planning stages. Driver scheduling is one stage in broader planning pipeline. Routes and timetable planning. Designing the service routes and schedules offered to the public. Vehicle scheduling, assigning vehicles to cover all trips in the timetable, at which bus, at which train, which driver covers what trip. So next we have the driver scheduling, assigning drivers to cover the vehicle operations, creating a daily shift for drivers, basically, in short. Then we have the driver rostering, organizing daily shifts into weekly rosters, including the rest days for each individual driver. And now we have this figure which basically tells us different stages of transport operation and planning. And you can see the figure 51.2 shows the stages in order. We usually decide vehicle assignment before driver shifts. Rostering comes at last. Driver grouping shifts into a week's work for each driver. You have the info flow. Each stage uses output from previous stage. After rostering, the plan is handed off to day operation. Then we have the integrated adjustments, though separated for manageability. These tasks are interrelated. And now we have the different types of transport services. You have the service variety, which is basically the bus and train services which come along in different areas like urban, suburban, rural. Then we have the urban commuter service, very frequent, many stops, lots of potential relief points en route, means huge combination possibilities for shifts. Optimal schedules often require short driving spells, but allowing very short spells multiplies the number of possible shifts, thereby increasing the cost, which we don't want. Next, you have the suburban and rural services, lower frequency, fewer stops, with longer runs and limited relief opportunity. The problem size is smaller, and scheduling might be easier for each route. However, the operators must mix service types. The same driver may cover a blend of urban and rural areas, and there may be multiple depots with different labor rules. Then we have the intercity and long distance train. Few cities, a few stops, but very long distances. So the unique challenge is drivers often ride trains as passengers. It's to get to where they need to start or end the shift. Scheduling must include these deadhead and travel arrangement for the drivers. And we have an overview of the scheduling research from the three eras. So the first is just the heuristic, which was from 1960s to 1980s. The solutions were developed by custom heuristic by operators, operation researchers working with transit agencies, and these were done in Co- Fort Cobra, I think, which is a very old, not that used these days language. And now then you have the second mathematical programming eras, which is from 1980s to early 1990s. With advancing techniques, researchers formulated driver scheduling as a set covering or inter programming problem. A landmark was the use of ILP in integer linear programming by Ryan and Foster, showing an optimal solution that can be found. Finally, you have the modern era, which is the meta heuristics and AI and combinational programming. So, more powerful computers and newer techniques led to revival of heuristics in the form of meta heuristics and later known as constraint programming. Genetic algorithms were first applied in mid 90s, followed by other methods like taboo search and simulated annealing. Hybrid approaches emerged, combining heuristics with ILP. So these methods could tackle larger instances and are more effective. And we have the bus and train scheduling research. So the common techniques, different constraints, methods developed by the bus driver have largely been applied to train driver scheduling as well. But train problems introduce extra constraints that require adaptation. Bus scheduling pioneered. Research into computer aided scheduling started with buses and urban transit. Many algorithm breakthroughs were demonstrated on bus systems. Train scheduling, systematic research on train crew gained momentum in the later 1990s. For a long time, rail crews were established mostly by manual or simpler methods, and but in 90s we saw that cases like the British Rail and other started adopting bus scheduling algorithms to trains. Key difference is that train drivers often work from numerous depots and may need to travel on train as passengers to relief points. This means that the problem can require integrating scheduling with timetable consideration for crew transfers. Buses usually have usually have drivers start and end at the same depot daily and don't involve mid shift travel on other vehicles. Also, train scheduling tends to have stricter union rules and can be more complex to roster across a week, whereas bus scheduling assumes drivers return home daily. So, now my friend Shivam will continue. Thank you for listening.
Hi everyone, my name is Shivam Patel and I will start with introduction of generate and select approach. In large transit systems, assigning drivers to shifts isn't just a matter of connecting trips. We break the task into two main phases, generation and selection. First, we generate shifts that are legal and realistic. Then, we pick the best combination of shifts to cover every scheduled trip exactly once while minimizing total cost. Formulating this as a set covering problem, gives us a solid mathematical framework to model and solve real-world scheduling challenges. Next is a shift generation phase. The shift generation phase is the foundation for all scheduling work. If this is done poorly, no amount of optimization later can fix it. Shifts must be comply with laws like mandatory rest periods, limits on total duty hours, and depot return policies. We construct shifts around relief opportunities, specific times and locations where a driver can be swapped. Continuous work stretches between ROs are called spells. Mapping these elements smartly at the generation stage is critical for later success. Next, we hop onto shift generation methods. In analytical construction, we intentionally limit ourselves to shift types we know work well, sacrificing some flexibility but keeping computations manageable. In contrast, uniform constructions generates every legal shift, capturing more possibilities but ballooning the problem size. TRACS2, a real-world scheduling tool, embraces uniform constructions, believing the computational challenges are worth for it for the superior schedule produced. The given figure visually shows the GAS pipeline. Vehicle work flows into shift generation and onward into optimization. Now let's look at the constraints involved in the shift generation. Constraints are absolutely vital to generating shifts that are workable in practice. Structure rules like maximum spells and maximum spread over limit driver fatigue and ensure compliance with labor laws. Time allowance rules protect driver welfare by enforcing sufficient meal breaks and realistic transfer. Skill-based constraints introduce an operational reality. Not all drivers can work every route or drive every type of vehicle, so we must carefully match qualification to shifts during generating itself. Now let's take a deeper look at a set covering problem. In mathematical terms, shift selection becomes a set covering problem. Each shift can cover some part of the overall work. We define binary variables, 1 if shifts is chosen and 0 otherwise, and aim to minimize the total cost across all chosen shifts. The constraint is simple yet powerful. Every piece of work must be covered. Understanding this formulation helps connect driver scheduling to broader fields like combinatorial optimization and operations research. You can take a look at the mathematical formulations that are being used. Now let's look at the challenges in large shift pools. When using uniform constructions, the number of feasible shifts grows explosively with the number of relief opportunities. If you have 1,000 ROs, even choosing start and end points in different combinations quickly leads to millions of possible shifts. This is not just a computational inconvenience, it is an operational barrier. There is no way to generate, store, or evaluate all possible shifts individually. Therefore, smarter methods like selective shift generation or iterative refinement becomes essential for handling real-world systems. Now let's take a look at the real-world constraints that are beyond the model. Beyond the elegant mathematical model, the real world introduces many messy complications. Depot rules means drivers cannot just start and end anywhere. They must typically return to their home base, limiting flexibility. Some drivers work split shifts, such as the morning peak and evening peak separately, requiring careful timing. Finally, not every driver is qualified for every route or vehicle type. Special certifications are needed or for certain services, adding further layers of complexity to feasible shift construction. So how do we optimize? So for that, let's take a look at the selection phase. Once shifts are generated, the selection problem formally becomes massive optimization task. Integer linear programming, which is an abbreviation for ILP, can find exact optimal solution, but only for relatively small to medium-sized dataset. In large real-world networks, heuristic methods like genetic algorithms and fuzzy simulated evolution are used. These methods don't guarantee the absolute best solution, but find high quality solution much faster. This trade-off between theoretical optimality and practical speed is common in large-scale scheduling. Once shifts are generated, the selection problem formally becomes a massive optimization task. In large real-world networks, heuristic methods like genetic algorithms and fuzzy simulated evolution are used. These methods don't guarantee an absolute best solution but find high quality solutions much faster. This trade-off between theoretical optimality and practical speed is common in large-scale scheduling. The next is genetic algorithm with combinatorial traits. GACT, or genetic algorithm with combinatorial traits, does not randomly evolve full driver schedules from scratch. Instead, it focuses on evolving smaller building blocks, such as sequences of spells called relief chains, that can be pieced together into final shifts. It uses the result of linear programming relaxation, a simplified version of SCP model, to bias evolution toward promising solutions. The given figure shows how spells are connected into partial relief chains that later become full shifts. This balance between randomness and structured guidance makes GACD a powerful scheduling tool. Now let's take a look at what fuzzy simulated evolution says. Fuzzy simulated evolution introduces graded evaluations of partial solutions. Instead of simply labeling a partial schedule as feasible or infeasible, FSE, or fuzzy simulated evolution, assigns a degree of goodness based on how close a solution is to meeting various criteria, such as minimum spread over, maximum work hours, proper break distributions, etc. This fuzzy evaluation helps the algorithm avoid getting stuck too early and encourages a broader exploration of the solution space. As a result, fuzzy simulated evaluation often finds better final schedules faster, especially when many conflicting constraints exist. Next is clone and reduce method. In extremely large problems, which is realistic and very likely to face in real world, even generating every possible feasible shift is impossible. Clone and reduce addresses this by initially generating a smaller, promising pool of shifts. Promising shifts are cloned, that is, copied and varied slightly, while weaker shifts are systematically removed. Over successive iterations, the pool remains manageable but still covers a broad enough set of possibilities. The given figure visually depicts this funnel-like narrowing or shifts options through cloning and filtering. Let's look at some case studies for clone and reduce. In a real-world example, a system started with about 2,339 relief opportunities. After 20 iterations of clone and reduce, the system focused on about 1,000 to 1,300 key opportunities. Importantly, the schedules generated after this pruning were not just computationally easier to manage, they were objectively better. Lower labor cost, better adherence to work regulations, and smoother operational executions compared to manual scheduling and compared to previous manually created schedules. So what are the limitations of GAS? While GAS has been very successful historically, it has some limitations. Chief among them is the assumption of fixed relief points. In practice, relief often happens within a time window. For example, a bus driver can be relieved anytime between 12 p.m. to 12:15 p.m. depending on the traffic. GAS does not adapt easily to this flexibility, sometimes resulting in impractical or costly schedule. Newer methods that allow dynamic, on-the-fly constructions are better suited to systems with such operational flexibilities. Newer methods that allow dynamic, on-the-fly constructions are better suited to systems with such operational flexibility. What should be the constructive approach? The constructive approach as used in systems like HACS builds schedules dynamically during scheduling process. Rather than enumerating all possible shifts first, it constructs feasible shifts as needed, adjusting dynamically to evolving conditions. Taboo search plays a critical role here. It keeps tracks of recent moves, prevents cycling back to previous solutions, and helps the system navigate towards better schedules over time. This allows it to adapt flexibly even in complex or disrupted environments. The constructive approach as used in systems like HACS builds schedule dynamically during the scheduling process. Rather than enumerating all possible shifts first, it constructs feasible shifts as needed, adjusting dynamically to evolving conditions. Taboo search plays a critical role here. It keeps tracks of recent moves, prevents cycling back to previous solutions, and helps the system to navigate towards better schedules over time. This allows it to adapt flexibly even in complex or disrupted environments. So what's the taboo search and how it is used in HACS? That we will look into the next slide, which is taboo search mechanism in HACS. Taboo search improves HACS by structuring the search process intelligently. After a move, such as swapping spells between drivers, the move is temporarily forbidden or taboo to avoid reversing it immediately. However, if a move, even if taboo, leads to a solution significantly better than the previous ones, the aspiration criteria allows it. This smart combination keeps the search dynamic and productive, steadily improving schedules without getting stuck. However, if a move, even if taboo, leads to a solution significantly better than previous ones, the aspiration criteria allows it. This smart combination keeps the search dynamic and productive, steadily improving schedules without getting stuck. What are the mode types that we have in HACS system and how these mode types helps to improve the schedules? HACS uses two primary types of modes to refine schedules: swap modes and relief reselection modes. Swap moves exchange spells between different shifts, helping balance working hours and avoid long idle times. Relief reselection moves adjust which relief time is chosen within a permissible window, often shortening duty times or reducing overtime. The given figure shows visual example of these two types of moves and how they affect the overall shift structure over time. Impact of this move is that they enable schedule to gradually evolve into more efficient and rule compliant configurations. What are some practical outcomes that we have and how we can compare what are the pros and cons of HACS and GAS? Both GAS and HACS have their place depending on the system being scheduled. GAS remains highly efficient in environments where everything is fixed, specific relief points, simple trip patterns, stable and daily schedules. GAS remains highly efficient in environments where everything is fixed and stable. However, as systems grow larger and more complex, or introduce flexibility like WROs, HACS dynamic constructive approach becomes essential. Choosing the right method depends heavily on the operational reality of the transit network being scheduled. Advantage of the HACS is that it handles flexible relief window naturally and adapt dynamically to system changes, disruptions, and large-scale instances. The strength of the GAS is that it is effective in environments where relief points and operational patterns are stable and highly predictable. Strategic choice for between both of them is that use GAS for small stable system, prefer HACS for large, complex or evolving system. Remaining part of the presentation will be presented by my teammate Mahak Patel. Thank you very much.
Thank you, Shivam. Hello, everyone. My name is Mahakbhai Patel. So now I would like to share a real-world example that perfectly illustrate how modern scheduling algorithm are being used, and that is the case of the Amtrak, the national passenger rail operator in the United States. The Amtrak operates over the 46 US state and covering over the 500 destination. And manages the thousands of daily train services, also scheduling the train crew like the engineers and the conductors in such a large and the complex network. It is the significant challenges. So to address this, Amtrak employs and the combination of advanced optimization technique, including the integer linear programming, which is also called as the ILP, and there is another method called the meta heuristic methods, integrated scheduling, then the real-time disruption management, and the multi-objective optimization. So now let's talk about all the algorithms and the techniques that's used by the Amtrak. So first of all, let's start with the integer linear programming, and that is used for the uh, crew assignment optimization. So like the Amtrak use the ILP to solve the core crew management assignment problem. Like IPL helps the assignment crew to train in the cost efficient manner while adhering to strict labor laws such as driving the hours limits and the rest periods. Also, it optimizes the guarantees all the rules are followed, minimize the cost like the overtime. And but however, due to the large scale nature of the problem, ILP can be a slow and inefficient when dealing with the millions of the variable, and which is where the meta heuristic comes in place. So meta heuristic, why meta heuristic is used? So actually the meta heuristic is used to balancing the speed and the effectiveness. Like the Amtrak utilized the meta heuristic like the taboo search, simulated annealing to complement the ILP. Like these methods provide a good enough solution quickly. So even when they are not mathematically perfect, this speed and adaptability allow Amtrak to adjust the schedules quickly in the real world scenario, such as the last minute crew sickness or the unexpected delays. And there is one more method called the integrated scheduling, which is used to coordinating the entire system. Like instead of the treating the crew scheduling, the train timetable, and the roster separately, Amtrak used the integrated scheduling, like to optimize all these elements are unified system. So this approach improve the efficiency, and that is what every operator needs, right? So reduce the deadhead trips, and then ensure the crew work assignments are fair and feasible, and which helps to maximize the resource utilization and reduce the operation cost. And there is another method called the real-time disruption method, like the quick adjustment. So in the events of the delay, like the when someone call a sick or equipment failure, Amtrak employs employs the real-time disruption management using the lightweight heuristic. So this fast algorithm enable the Amtrak to quickly to reassign crew or the adjust scheduling. So which is enabled ensuring the minimal disruptions and keeping the operations on track. Now, the Amtrak used for the balancing multiple goals. Amtrak used the multi-object optimization. Like the Amtrak system is the built on the multi-object optimization, where the goal is not only to minimize the cost but also the distribute the work fairly among the crews, minimize the unnecessary travel, and also ensure the schedule robustness against the delay. And this ensures the balance between the efficiency, fairness, and I can say the adaptability, or you can say the robustness. So at the end, in conclusion, I can say that the Amtrak approach to schedule is a perfect example of how modern optimization algorithms are applied in the real world scenario, like the integration of the ILP, meta heuristic, and the real time decision making that enable Amtrak to manage its complex operation efficiently, and ensuring that the train run on time, crew are assigned fairly, and the system can quickly adapt to unforeseen disruption. And this is the powerful demonstration of how theoretical scheduling techniques are crucial for the source success of the large complex transport network. So now let's focus on the integration of various scheduling tasks, like the challenge and also the challenges faced by the traditional method, and how the modern techniques are changing the game. So let's start with the traditional approach, like the how here is historically vehicle driver and the roster scheduling have been treated as a separate task. Each team work in the isolation. The vehicle planner focus on the vehicle assignment. The driver team handle the shift scheduling, and the roster team play a weekly pattern. The issue with this approach is that the optimize the one area may lead to the inefficiency down the road. For example, a well-optimized vehicle schedule might clash with the driver availability or the leave some shift unfilled. And why does integration matter? So simply put, the vehicle assignment to directly impact the driver scheduling. If a bus finish 10 minutes earlier, that if affects the next driver shift and could lead to the disruptions. So the rostering is another piece. So weekly shift must respect the scheduling patterns of the driver to avoid the burnout or dissatisfactions. And then what's the solution, right? So by integrating the optimization, we can achieve these things like the when the vehicle blocks driver shift and the weekly rosters are well considered simultaneously, we achieve much better solution. This approach minimize the number of driver needed, create the smoother rosters, and reduce the overall cost. More and more transit agencies are investigating in the integrated the planning software to achieve this reason. So modern tools like the Trebsi and the Optibus are built specifically to integrate these elements and offering the smarter, more efficient planning. And it's all about the working together, not in silos. Now let's move on to the challenges of the method used to solve the scheduling problem. Like the one common technique is the integer linear programming, that's also called as the ILP. ILP provide the mathematical guarantee for the best solution. It is the perfect for the small scale problems. But here is the catch. So real world scheduling ensure the involve the millions of variable, and ILP simply struggle to scale to that level. On the other hand, we have the meta heuristic, so like a genetic algorithm, taboo search, simulated annealing. These methods are much more faster and adaptable. They may not always find the optimal solution, but they find a very good solution quickly, which is often more important in the uh, I can say the real world applications. There is one hybrid approach is there that is based for both the worlds. By using the meta heuristic to generate the high quality candidate solution and then solving the smaller ILP over this candidate, and we can get the near optimal solution without that heavy computational cost. In practice, so a transit agency care more about the solution that are good and the fast rather than the perfect and slow. And there is where the hybrid approach is increasingly the go with the strategy. Now let's talk about why the robustness and flexibility needed and how to use. So disruptions are the part of the life in the public transports. Drivers get sick, vehicle breakdown, a traffic jam happen. So how do we handle this type of the disruption? So first of all, a robust schedule anticipate this problem. It include the buffer times between the trips, spare drivers on the standby, and the frequent relief point for flexibility. This ensure that the even when the things doesn't go as a plan, the system can absorb the shock. The second one is the flexibility. So the flexibility is the another key feature. Multi-depot flexibility allow driver to work from multiple depot, like which give them a more options, swappable shift that make it easier to cover the shift if someone calls in sick. This feature not only reduce the service disruption but also improve the driver morals and the boost on time performance for the passenger. So in short, I can say that the building the resilience into your scheduling system is the essential for maintaining the smooth operation and keep both the driver and the passenger happy. Now let's move to the physical constraint and the preference modeling. So, how the real world scheduling isn't just the black and white. Some rules are strict, but the others are feasible. Like I can say flexible. That is where the physical constraint and the preference in modeling comes in. So scheduling isn't just the black and white as I discussed. There are hard constraints like a legal limit on the driver's hours per day, a soft constraints like a driver prefer shifted start time. Fuzzy modeling help us to navigate this complexity. Instead of the treating the preferences as a absolute yes or no, fuzzy modeling introduce a degree of satisfaction. Like for example, if the drivers prefer a 7 a.m. start, but a 6:50 a.m. or the 7:10 start might be acceptable, but with the slightly lower satisfaction. But this allow for the better flexibility and the smoother schedules. So by using the fuzzy modeling, we can better balance the company's need with the driver preferences, leading to a happier driver and the fewer conflict over the scheduling. In turn, this helps to improve the retention rate and create the schedules that are more adaptable to the real world. Next, let's talk about the real-time scheduling. In the perfect work, everything goes uh, according to the plan, but in the real world disruptions happen. A driver might call in the sick or just 10 minutes before their shift. or there might be a major accident causing delays. So real-time scheduling need to be quickly reassign the driver and the vehicle. This requires the rapid computational and the integration of the real-time data like the GPS and the traffic feeds. So in model control rooms, use the mobile alert to notify drivers immediately about the changes, allowing them to adapt quickly. So in this type of situation, the key is to speed and practicality. You need to make quick decision without trying to optimize for the perfection, like the lightweight heuristic as we discussed earlier, that combined with the AI assistant dispatching help system to adapt on the flying. Then I can say the minimize disruptions and ensuring the service continuity. Now let's take a step further and discuss the multi-object optimization. So I can say in the past, in the old fashion, the most scheduling focus on to minimize the cost, specifically the driver cost. However, today's system need to be balanced the multiple objects. It's not just about the cost, it's about the fairness, resilience, and the driver satisfactions as well. So the multi-object method allow us to find the what's the known as the Pareto optional solution. So this solution represent the trade-off between the conflict object. For example, optimize for the cost might reduce the driver satisfactions, while focusing on the fairness might be increase the operational cost. By visualizing this trade-off through the Pareto fronts, decision makers can select the best solution depending upon the day or day's priorities. So in practice, this means schedules are not only more robust and the worker friendly, but also they align better with the company's social responsibility goal. So, as the integrated multi-criteria decision making, which is also called as the MCDM, become the more popular, where we see a shift towards the more human-centric scheduling models in the public transport sector. And at the end, I can say that the driver scheduling, or I can bus or train scheduling, is becoming the more sophisticated. It is no longer just about the minimize the cost. It's all about the creating the smarter, more integrated, and the more resilient system. Like the modern approach prioritize the integration across the all the scheduling tasks, robustness in the face of disruption, real-time adaptability, and the fairness for the workers as well. So as the research continue to evolve, we are shifting towards the multi objective models that consider the needs of both the companies and the employees. And the future of the scheduling is not only about the efficiency, but also about the creating the system that works for everyone. And for the references, we use these references to prepare for these presentations. And yeah, thank you so much everyone for your time, and we will love to answer any of your questions. So if you have any question, please drop into the discussion box and we will happy to answer your question. Thank you so much everyone.